Ask yourself the biggest question there is, where did everything come from? We all know the answer is the Big Bang. About 13.8 billion years ago, the universe as we know it began. This moment marked the start of space, time, and matter. It's the origin story that science tells us about the cosmos. But whenever we hear about a beginning, our brains naturally jump to a location. If something starts, it must start somewhere. If you light a match, the fire starts at a point. If you throw a ball, the movement starts from your hand. So if the universe started, where is the center of the Big Bang? Here is the cosmic twist. The universe has a clear, documented, physical beginning in time, but it has no center in space. That single contradiction challenges our fundamental everyday intuition about how things work. The concept of a Big Bang beginning originated with calculations decades ago. Thinkers like George Gamow and his student Ralph Alpher calculated the primordial abundances of light chemical elements, focusing on what was created when the universe was incredibly hot and compressed. This work laid the groundwork for the understanding that the universe had a definitive start approximately 13.8 billion years ago. Their theory also correctly predicted that leftover energy from this dense, hot beginning should still exist everywhere as weak thermal microwave radiation, which we now call the cosmic microwave background, CMB. This eventual discovery confirmed the universe's beginning. But here is where our intuition misfires. We assume the Big Bang was a physical explosion, like a bomb going off in a specific spot in pre-existing space. That assumption immediately sets up the need for a center, a point from which everything flew outwards. That assumption is wrong. The Big Bang was not an event in space, it was the start of space and time themselves. All of the universe we can see, and likely all that exists beyond our horizon, was contained within that initial state. It was a beginning of time, not a launch point in geography. We are searching for an epicenter when the event happened under every single point we currently occupy. The idea of a black hole is similar in complexity. Black holes are regions where the gravitational pull is so strong that nothing, not even light, can escape. The theoretical framework for black holes, developed from Einstein's general relativity, describes an event horizon, the boundary of no return. However, the black hole itself is defined only by its mass and spin. It is defined by the bending of space-time, not by a physical surface in the traditional sense. Just as a black hole is defined by the distortion of space-time rather than a physical object, the Big Bang is defined by the origin of space-time rather than a location. This reality forces us to abandon the simple picture of an explosion scattering debris. Instead, we must picture space itself, stretching, carrying matter along with it, and this process of stretching is happening uniformly, everywhere, right now. When we say the universe has a beginning, we are defining a finite period for the existence of space-time. It means that there was a transition from a state where all matter and energy were concentrated into an intensely hot, dense condition to the expanding, cooling cosmos we observe today. This event, documented through the calculations of early physicists and the eventual detection of the relic radiation, set the age of the universe at roughly 13.8 billion years. However, this beginning is difficult to describe fully because our most reliable physical laws fail at that extreme point. Einstein's theory of general relativity, which describes gravity as the curvature of space-time, predicts a mathematical singularity at the Big Bang. This singularity is not a physical location you can point to, rather, it is the theoretical boundary where time itself began. For anything falling into a black hole, the singularity becomes an unavoidable moment in time, marking the end of that object's ability to affect the external universe. The Big Bang was the universal, simultaneous start of that cosmic timeline. The profound significance of this beginning is that it dictates the ultimate structure and behavior of the universe. The simple fact that structure formed at all, that stars and galaxies exist, proves that the universe started in an incredibly ordered state, or what physicists call low entropy. If the universe were infinitely old or started in a disorganized state, it would have long since settled into a featureless, hot soup. The sheer improbability of this original state suggests the Big Bang was the ultimate low-entropy starting point. The physical evidence of this beginning is embedded in the cosmic microwave background, CMB. The CMB is the oldest light that could travel freely after the Big Bang, a point in time when the universe cooled enough for light to stop scattering off plasma. The CMB acts like a photograph of the universe at 380,000 years old, confirming that the early conditions were consistent and synchronized across the entire expanse. This finite beginning immediately answers the ancient puzzle of why the night sky is dark. Not enough time has passed for the light from all potential stars in an infinite cosmos to reach us. The age of the universe sets the limit on the size of the observable universe. This boundary is defined by how far light has traveled since that beginning, not a physical edge of existence. The beginning of the universe is a concept about time, and the age of the universe is the physical metric that dictates everything we can see today. The confusion about a center stems from misunderstanding how expansion differs from an explosion. We must replace the familiar image of a bomb with the abstract concept of stretching space-time. Our intuition tells us that an explosion must have a central point where the event began. In that scenario, matter moves outward into pre-existing space. The velocity of the fragments decreases the farther they get from that center due to energy loss and resistance. This process would naturally result in chaotic motion and non-uniform gradients across space. The Big Bang and subsequent cosmic expansion are fundamentally different. The Big Bang did not have a central point. The origin was simultaneous across all space. The event was not matter flying through space, but rather space itself, stretching and growing. Instead of the velocity decreasing with distance, as in a conventional explosion, the velocity of receding galaxies increases proportionally with their distance from the observer, a key part of Hubble's law. This happens because more space is being created between distant objects, carrying them away faster. The differences are stark. While an explosion creates non-uniform chaos, cosmic expansion leads to remarkable uniformity. The observational evidence confirming expansion, such as cosmological redshift, where light is stretched universally as it travels through expanding space, is consistent with a universe that is stretching everywhere at once. Furthermore, the existence of the incredibly uniform cosmic microwave background, CMB, proves that the early universe was synchronized and smooth, not exhibiting the chaotic non-uniform gradients expected from a central explosion. This uniformity is a necessary condition of the Big Bang theory because if the universe were clumpy or centered like an explosion, the laws of physics and the resulting cosmic structures would be unstable. The core idea is that we are not observers watching shrapnel fly past us. We are observers embedded within the stretching medium itself, a medium that began synchronously everywhere. To grasp the abstract idea of expansion without a center, cosmologists use the balloon analogy. This analogy helps shift our thinking away from 3 dimensions and into the dynamic geometry that governs the cosmos. Imagine a balloon representing all of space. We are restricted to living only on the 2-dimensional surface of the balloon. Dots are drawn on the surface, representing galaxies. As the balloon is inflated, the rubber surface, which is our space, stretches. The distance between the dots increases because the rubber is growing. If you observe this from the perspective of any single dot, you would see every other dot receding from you, and the dots that are farthest away would appear to be moving away the fastest. This uniform recession is exactly what we observe with Hubble's law. The analogy perfectly illustrates 2 key points about our universe. First, there is no center. No single point on the 2-dimensional surface can claim to be the center of the expansion. Second, the recession is uniform. Every observer sees everything else moving away, confirming that the stretching is everywhere. However, the balloon analogy has critical flaws that, if misinterpreted, lead right back to the center misconception. The most important flaw is that the balloon expands into the air, implying a 3rd dimension and an exterior void. Our universe does not expand into anything. It creates its own space. We must ignore the volume inside and outside the balloon. Our reality is only the stretching surface. Similarly, we must ignore the misconception that the Big Bang happened at the center inside the balloon. The Big Bang happened on the surface, meaning it occurred where we are now. The expansion is defined by the internal stretching of spacetime itself, not by an external reference point. This analogy is merely a helpful tool to discard our 3-dimensional, explosion-centric bias. The uniformity of the expansion, meaning why every location sees the same expansion, is a direct consequence of the physical properties of the cosmos on the largest possible scales. This concept is formalized by the cosmological principle, which holds that the universe is homogeneous, uniform density, and isotropic, looks the same in every direction. If you, as an observer in the Milky Way, measure the rate at which distant galaxies are receding from you, you find it matches Hubble's law. If you could magically transport yourself to a galaxy 10 billion light-years away and perform the same measurements, you would observe the exact same phenomenon. All other galaxies would be moving away from you at rates proportional to their distance. This symmetry is what prohibits the existence of a center. The uniformity of expansion is confirmed by the near-perfect smoothness of the cosmic microwave background, CMB. The CMB is the ancient radiation left over from the Big Bang, and its temperature is almost identical everywhere in the sky, clocking in at about 2.7 Kelvin. This smoothness proves that the early universe was in thermal equilibrium. If the universe were not expanding uniformly, or if it had a center, the CMB would display large, noticeable temperature gradients. The physical mechanism that ensures this uniformity is cosmological redshift. As light travels from a distant galaxy to us, the expanding space stretches the wavelength of the light. The further the light has traveled, the more stretching has occurred, and the greater the redshift. Since we observe this effect consistently in all directions, and the recession velocity correlates directly with distance, Hubble's law, it confirms the universal stretching of space itself. If the universe had a center, say point C, observers far from point C would measure different rates of expansion depending on whether they look towards C or away from C. The fact that all measurements are consistent regardless of the observer's position validates the cosmological principle and the non-central nature of the Big Bang. The initial state of the universe, smoothed out by the rapid expansion of inflation in the first fraction of a second, guaranteed this symmetry. The abstract nature of expansion leads to repeated attempts to fit the event into a familiar, localized framework. Addressing common misconceptions about where the Big Bang happened is essential to truly understand the structure of the cosmos. A common misconception is that the Big Bang was a physical explosion, and the fastest-moving galaxies are at the edge. This confuses expansion with an explosion. In an explosion, matter moves through space, with the edges being the fastest-moving material. In expansion, space itself is growing. The speed is proportional to distance, and distant galaxies recede faster because more space is being created between us and them. There is no edge in the traditional sense. The universe is likely vast and potentially infinite. Another misconception is that we can point to the location of the Big Bang somewhere in the sky. The Big Bang happened everywhere. Every location in the present-day universe, including our solar system and galaxy, was compressed into that initial hot, dense state. If we could look back 13.8 billion years in time, every direction would lead to that point of origin. The expansion of space has simply carried that initial synchronized state outward uniformly. Finally, the misconception that the expansion is slowing down is false. Observations confirm that the expansion of the universe is not only continuing, but is accelerating. This acceleration is attributed to dark energy, which seems to be an inherent property of space itself, pushing volumes of space apart. This dark energy ensures that the universe continues to stretch and that its uniformity is maintained across vast scales. The uniform recession of galaxies dictated by the cosmological principle is the most powerful constraint on our understanding of how the universe grows. The assertion that there is no center is one of the most firmly established conclusions in modern cosmology, supported by direct astronomical evidence confirming universal symmetry. First, the cosmic microwave background, CMB, isotropy is critical evidence. The CMB is the thermal radiation remnant of the Big Bang, and its temperature is incredibly uniform, approximately 2.7 Kelvin across the entire sky. This near-perfect uniformity proves the early universe was in thermal equilibrium. If there were a center point, energy gradients would have created large, discernible temperature variations across the cosmos. Second, Hubble's law consistency is essential. The observation that distant galaxies recede from us at a speed proportional to their distance is consistent regardless of the direction we look. This law, based on measuring cosmological redshift, the stretching of light wavelengths by expanding space, is the signature of a uniform stretching of the space-time fabric everywhere. An explosion from a center would create a complex non-linear flow pattern. Uniform recession confirms the lack of a center. Third, the distribution of distant objects is uniform. Cosmologists study the distribution of structures like galaxies and quasars across the sky, and these ancient, powerful structures are observed to be statistically spread evenly in all directions. If the Big Bang had a center, these structures would cluster or align in a way that would reveal a directional preference, which we do not see. Finally, the lack of velocity drift is telling. If the Big Bang had a nearby center, our Milky Way galaxy would be experiencing a significant velocity drift, or push, away from or toward that center point. While the Milky Way does have measured motion relative to the CMB, this motion is attributed to local gravitational forces from nearby galaxy clusters, not motion relative to a cosmic center. The conclusion that there is no center is inextricably tied to the concept of isotropy and homogeneity. These observational facts form the bedrock of modern cosmological theory. If the universe was structured around a central point, every established pillar of modern cosmology would change. The consistency and reliability of astronomical data would entirely disappear. If a center, point C, existed, observations would become anisotropic, direction-dependent. If we look toward point C, we might measure a different recession rate or expansion velocity than if we looked away from it. Hubble's law would fail to describe the universal expansion, and we would have to account for our specific distance and orientation relative to point C. The physical laws that apply in our area might not apply somewhere else, fundamentally challenging the assumption of universal constants. Furthermore, the CMB would be non-uniform. The ancient radiation would look like a bullseye with severe temperature and density gradients centered on point C. The cosmic synchronicity that allowed the early universe to achieve thermal equilibrium everywhere would be absent. This would force us to discard the idea of inflation, which was developed to explain the CMB's smoothness. The physical consequence of a center is catastrophic. The uniform expansion rate and the initial smooth state are necessary conditions for a universe that is stable and develops complex structures. If the universe were uneven or centered, the resulting non-uniform gravitational pulls would lead to chaotic evolution and violent collapse in some regions, preventing the formation of stable, long-lived stars and galaxies. The universe's current age and the steady progression of time itself rely on the smooth, low-entropy starting point guaranteed by a non-central beginning. The fact that our universe is vast, stable, and predictable is a direct result of the cosmological principle holding true, proving there is no center. The universe's beginning is a beginning of time, an era dictated by physics, but without a geographical center. What does it actually mean for the universe to have a beginning? It means there was a transition point from a state of singularity to a state of expansion. Before this event, our current theories of general relativity break down. The most we can say is that our reality is tied to a finite lifespan of 13.8 billion years. This beginning gave us the low-entropy, highly ordered starting conditions necessary for stars, galaxies, and life to form. This beginning is not a flaw in the universe's geometry, but a reflection of how space-time is curved and dynamic. The discovery of gravitational waves confirms that time and space are woven together into a flexible fabric. When massive objects collide, they send ripples through this fabric, stretching and squeezing space and time simultaneously. A black hole demonstrates this link perfectly. It is an object made of pure, warped space-time. For anything falling into a black hole, the singularity at the core becomes a mandatory moment in time rather than a place in space. Once you cross the event horizon, you are moving toward the singularity, not through distance, but through time. The Big Bang was the universal, simultaneous start of that timeline for all of existence. The uniform expansion confirms that every observer everywhere is equally immersed in this timeline, seeing the same overall conditions in the universe. If a center did exist, it would shatter the isotropy seen in the CMB and create massive density variations. It would destroy the basis of our cosmological models and force us to accept that position in space dictates the laws of nature, a concept incompatible with the symmetry observed in the cosmos. The greatest evidence that there is no center is simply that the universe looks and behaves exactly the same, no matter where we look or where we are. The universe presents us with this beautiful, frustrating paradox: a definitive birthday, but no fixed address. The Big Bang was confirmed by the uniform echo of the cosmic microwave background radiation, which tells us that the early universe was astonishingly smooth and highly ordered. This uniformity is the critical reason why no location can claim to be the center. The expansion is the stretching of space itself, carrying every galaxy away from every other galaxy, without any single origin point. The fact that every point appears to be the center and every observer sees the same uniform expansion, Hubble's law, is the most profound proof that no true center exists. If a center did exist, the consistency of the entire cosmos would break down, and the universe would be a chaotic, unbalanced mess. The simplicity of this synchronicity that everything began everywhere at once and has expanded uniformly ever since is so precise that it required a massive, sudden event called inflation to iron out the details in the first fraction of a second. If you want to understand space like a NASA-level analyst, quick without studying for years or paying thousands for a university degree, we have a free community that will help you. Link is below. The universe is vast, and our place in it is not special, but the rules that govern it are universally applied. Every time you look out into the night sky, remember you are seeing proof that the beginning was a shared moment of time, not a lost geographical location. That uniformity, that cosmic smoothness, is itself an immense mystery. Why did the universe begin in such a synchronized, ordered state? Why is it so even? If you want to know how scientists figured out why the universe is so smooth and what that tells us about the structure of reality, click here to Why the Universe is Too Even video.